Welcome students. We are back with another lesson. In this lesson, we'll continue with our chapter 11, Dual Nature of Radiation and Matter. In this lesson, we'll discuss experimental study of photoelectric effect. So first let's discuss about the apparatus for your photoelectric effect. In your photoelectric effect, you have a evacuated glass tube on which you have a quartz window. From here, the radiation will enter this glass tube. Next, you have a photosensitive plate which acts as your cathode. And then you have a collector plate which acts as your anode. Next, here you have a microammeter which detects the current. And then here you have a voltmeter which detects the applied voltage. And then here you have a potential divider which controls the potential applied to this whole circuit. Okay, and then you have a key here, and finally here, and then here you have a battery. From this battery you apply a potential to this potential divider which gives the potential to all these components out here. The applied potential is being measured by this voltmeter. Fine. Now let us suppose you apply some potential. This potential is measured by your voltmeter. Now if you apply potential here, what happens? This green line, okay, check this collector, the one which is connected with the green line, the one which is connected to the collector will become positively charged plate. Fine. And this one, okay, the one which is connected by the red one, your photosensitive plate, will become a negatively charged plate. Your cathode will become negatively charged. Now why did I apply this potential? I have applied this potential so that if there is any free charge inside this glass evacuated tube, okay, it will move from the negative to the positive terminal. So if you consider you have a electron somewhere here, so if you have a negatively charged free electrons, okay, this electron will be repelled by this cathode which is negatively charged plate, and it will be attracted by your anode which is positively charged plate. So you have applied an electric field. You have given direction to this electron to flow from your negative plate cathode to your positive plate anode. So this is the direction of the applied field. Now let us consider you apply some source. You allow the light to pass through this quartz window and fall on this cathode. So as soon as the light from the source falls on the cathode, what happens? The electrons are emitted from this photosensitive plate, and this emitted photoelectrons move towards your collector. Now collector collects this photoelectron, and if the collector collects this photoelectron, what happens? The current starts to flow through the circuit. So you will get a reading here. So you will measure some current at your microammeter. Fine. So you will measure some current at this microammeter. So this whole phenomenon where the source of radiation falls on this cathode, electrons are emitted from this cathode, this phenomenon is known as your photoelectric effect. Fine. Now let us increase the intensity of the radiation coming from this source. So if you allow more intensity to fall on this cathode, more amount of photoelectrons will be generated, or it will be emitted from this cathode. Right? So what you can conclude, the more the intensity flows, the more the electrons are generated, the more current will be detected at your microammeter. So let's plot a graph. On the x-axis, I'll write down my intensity of light. On the y-axis, I'll write down the photoelectric current. So if I increase the intensity of the light, if I increase the intensity of the radiation, what happens? The current, the photocurrent also increases. So you get a linear graph, fine, a straight line graph. As the intensity increases, the photocurrent also increases, fine. So this is your first study of your photoelectric effect, or this is the effect of the intensity of light on the photoelectric current. So this is your first observation. So you can write your first observation that for a given photosensitive material and the frequency of the incident radiation for this specific type of photosensitive material and what is the frequency of this incident radiation above the threshold frequency. Okay, this term I will explain you later. For now you just consider threshold is just some value of frequency. The incident radiation should have a frequency greater than your threshold frequency, fine. So coming back, above the threshold frequency, the photoelectric current is directly proportional to the intensity of the light. So we have seen in from our first experiment that if I increase the intensity of the light, this brightness, if I increase the brightness, what happens? The photoelectrons generated increases, and in turn the current detected also increases. So the photoelectric current is directly proportional to the intensity of the light, or I can also say the saturation current is directly proportional to the intensity of the light. Okay, I will explain this term saturation current later. Okay, for now also you can consider this as a constant value of a current. Okay, you can just for now you can just simply assume it is some value of a current. Okay, for now you just focus that if the intensity of the light increases, the current also increases, fine. So now consider, suppose you have an intensity falling on this cathode, the photoelectrons are generated and the photocurrent is detected. Now let us suppose we increase the potential, we increase the applied voltage. We increase the applied voltage keeping the frequency of the incident radiation constant. So now if you increase the voltage, what you notice is that more potential will be applied here. If more potential is applied here, that means it will apply more electric field. If it apply more electric field towards this positive direction, that means more photoelectrons will be generated. So if more photoelectrons are generated, that means the current, the photocurrent also increases, right? Therefore I can notice that if I increase the potential further, more photocurrents will be generated. If I increase the potential further, more and more photoelectrons are detected at this collector, fine. This continues till a potential at a particular value of the potential. Okay, or instead of potential, let us say it takes place till a constant value of a current. That means let us focus at the graph. Okay, so look at this graph. So what did I say? If I increase the anode potential, the current also increases till a particular value of the current. Okay, at this value of the current, what happens? If I increase the potential further, my current does not increases, rather it becomes a constant. Okay, fine. So you'll see a constant straight line curve. So what you notice is that if I increase the applied voltage, the current increases, which can be seen from this part, fine. But after this point, okay, after this point, okay, let me just make this one a straight line, fine. After this value of current, what happens? The current becomes constant. That means no matter how much I increase my potential, the current will be same, and this constant value of the current is known as your saturation current, fine, and it is denoted by I. In suffix you can write saturation, SAT, fine. So this is what happens if I increase the applied voltage. Now let us decrease the potential. Now let us start decreasing the potential. Now if I decrease the potential, what happens? The photoelectron generated also decreases. So if I decrease the potential further, less photoelectrons are generated. Fine. Now let us say at zero potential, and the potential is zero, at this point there is a current flowing. That means there are photoelectrons generated. Now this photoelectron generated are only because of this source of light. Whatever radiation is falling, it generates the it generates the photoelectrons. This photoelectrons passes through this ammeter, which in turn are detected as the current. So at zero potential, there is some amount of current flowing through the circuit. Now what happens if I decrease it beyond, further than zero? What do you mean by if I decrease it below zero? Okay, this is zero. If I go below zero, what happens is that instead I cannot go negative. So what I will do, I will make this negative terminal positive, this positive terminal negative. So if this is the case, that means I am decreasing my potential beyond zero. Fine. I am retarding my potential. That means this potential is decreasing and it is going minus zero. Fine. Or since we cannot apply minus, so I have changed the terminal. The negative I made positive and the positive I have made negative. Now if I decrease it further behind the zero, okay, what happens? The potential at this cathode starts to increase and the potential at this anode starts to decrease. Fine. So if this happens, that means what happens? This part will become positive, this one will become negative. But since the light is falling on this plate, the intensity is falling on the plate, the energy which is gathered by the electron of this photosensitive plate, these electrons, okay, they still have some more energy as compared to your potential. Fine. They still have some slightly higher energy to overcome this potential. So what happens? Still the photoelectrons will be generated, but it will be very few in number. Only the ones which have a potential higher than V. Only those electrons, only the electrons having energy greater than this potential, only those electrons will be generated. And if this generated electrons flows through this microammeter, what happens? The current will be detected, but it will be less. So what happens? If I decrease the potential, what happens? The current also starts to decrease. Fine. So if you decrease the potential, the current also decreases till a specific value of the potential. At this specific value of the potential, what happens? There will be no electrons emitted. That means the intensity supplied will not be able to overcome the applied potential. So at that particular potential, at this point, fine, at this point, what happens? No photoelectrons will be generated. If no photoelectron generated, will you detect any current? So at this point, no current will be detected. So I can say at this value of potential, let us give this potential a name. So at V0, which is your stopping or your cutoff potential. So at cutoff potential, no photocurrent is generated. Can you see? The photocurrent is zero. Fine. So we can write down our next observations. So this is your first observation. The photoelectric current increases with the increase in the accelerating potential till a stage is reached when the photoelectric current becomes maximum and does not increase further. Okay, this is further. So does not increases further with the increase in the accelerating potential. So this one, okay, this part of the curve. So as you increase the potential, the current also increases till it reaches a particular value of the current, beyond which the current does not increases further. And this maximum value of the photoelectric current is known as your saturation current. And this maximum value is known as your saturation current. Fine. And your second point, the value of the retarding potential at which the photoelectric current becomes zero is called cutoff or stopping potential for the given frequency of the incident radiation. So the value of the potential at this point, at minus V naught, what happens? The photoelectric current becomes zero. So this value of the potential is known as your cutoff and your stopping potential. Fine. So that's it for today's class. Thank you. And if you have any confusion, please don't hesitate to ask. I will re-explain it to you again. And in our next class, we will discuss some more on the effect of potential, and then we'll see the effect of the frequency of the incident radiation on the stopping potential. Fine. So that's it. And again, thank you.